MATLAB. Okay, we have home here. Okay, you can see there are many menus here. New script, new open, import data, right? Simulink, right? Preference setting or etc. Right. So right on the second tab you have plot. Okay, so you can plot different different type of graph. Okay, and then there is also an apps which no, before this is called as a toolbox. Okay, but nowadays they call it as apps. Okay, there is something that you can use together with your programming. Okay, depend on what project you are working on. Right, but basically the interface will consist something like this. Okay, you can see the folder. Okay, this is the current folder, which is here I open the MATLAB folder. Okay, so you should make sure that your current folder is where is the folder that you keep all your data, all your file, all your project in. Right, in here is the command windows. Okay, this is where we type command. Okay, whether you want to plot, whether you want to do arithmetic operation and etc. Okay, this one here is workspace. Okay, workspace is where MATLAB show us all the variables that we use. Okay, and also the value. Okay, and then this one here is the command history. Okay, so sometimes we don't need this command history, but it also help us to recheck the step that we have done. Okay, so for control engineering, right? First, I will introduce to you about transfer function. Okay, so we already learned about transfer function. Okay, the transfer function is normally represented by a numerator divided by denominator. Right? So in MATLAB, okay, we need to define what is our numerator and what is our denominator, so that will be become the transfer function of the system. Right? So once we have the transfer function of the system, we can do the time response analysis, and we can plot. Okay, we can do all the time response analysis, frequency response analysis, and etc. Right? All right, so let's say let's say we have a transfer function. Let's say our transfer function G is equal to okay, G is equal to let's say 5 over 0.5 s plus 1. Okay, so this is the first order transfer function. Okay, so by looking at the transfer function, we know that the time constant is 0.5. It should reach 0.5 second. It should reach a time 0.632% of final value at 0.5 second. And then the gain is 5, meaning if you apply unit step input, then it should be 5. The final value should be 5, right? Okay, let's see how we can use MATLAB in order to do the step analysis. All right. Okay, first let's declare our our numerator. Okay, so we just give num equal to 5, right? And then denominator, then you can put any names actually. Then is equal to, it is a metric there. So it is 0.5 s and then 1. Okay, so here in workspace, we can see that numerator is 5 and denominator is 0.5 second. Right. So if we want to do the step analysis, we can apply step num numerator versus denominator. Okay, so if we type this command, so if we plot the step response of the system, take some time to plot. Okay, right. So we can see here, this is the response. Right, we can see the final value is 5. Okay, because the gain is 5. Okay, k multiply with unit step input. So the final value is 5, and then at 0.5, okay, okay, so at 0.5 it should reach 0 30 63.2% from 5. Okay, so I believe it is around here. Okay, mana dia punya line. Okay, but basically I want to read the data actually, but I don't know why it's not. Okay, basically we can move the cursor and read the data. Okay. All right. So this is the command for step input. Okay. All right. Check this one here. Okay. Right. So for this command, we can use, we can represent the system in terms of S, right? So we already defined the numerator is 5, the denominator is 0.5 and 1. And then you should write this command first, right? To represent the S is equal to the Laplace term, okay? So then when we define G, the transfer function for G is numerator and denominator. So if we plot the continuous transfer function. All right. Lagi ke situ. Okay. Let's try impulse. right? So this is the response to the transfer function when we apply impulse input. Okay, impulse input. So this is uh, all the command that I present here is for the zero initial condition, right? Meaning you start at zero, all the initial condition is zero. Same goes to the impulse input, all the initial condition is zero, right? So this is how the system will respond when you apply a unit step input, a unit impulse input, one, then it will multiply to 10 and then it slowly reduce to zero. I'm not sure about RAM. There's no function for RAM input, right? So meaning we cannot type the RAM input or RAM input in MATLAB. So meaning you need to use Simulink in order to simulate the behavior of the system. Other than that, later when you learn about frequency response, okay, later you will learn about Nikes. So you can also plot the Nikes diagram. Okay, so the command is Nikes. Later we will learn about Nikes diagram here manually using paper. But this is the command if you want to plot the Nikes plot using MATLAB. Okay, and then the other one is I think root locus. Okay, in chapter 4, after the semester break, you're going to learn about root locus. So, okay, so this is the root locus for the transfer function just now, 5 over 0.5 s plus 1, right? So it will provide you this kind of root locus. Right, but I just want to show you the command here, Nikes, the transfer function, root locus, transfer function, and the last one that you're going to use is boot plot. Roots. All right. Okay. The command should be not capital B. So it's a small b, B-O-D-E, body plot. So we can see the body plot for the system, right? Basically, this is the thing that you learn in MATLAB. So the time response, which is step input. Normally you use step input and impulse input. And then in the frequency response, in the stability, you learn about root locus. So you're going to use the command root locus, right? And then in frequency analysis, we have two methods. You can either draw the Nikes plot or draw the boot plot. Okay, later you will learn about this and learn how to interpret the diagram. Right, so here I'm just showing you the command that you can use in MATLAB in order to plot all the analysis that you're going to do. Oh, what else in MATLAB? Nikes, apa lagi? Okay. Okay, this is one more thing. Okay. Okay. So I'm going to get the closed loop transfer function for the system. So let's imagine 5 over 0.5 s plus 1 is only a system. Then I want to add a controller and then a feedback loop. Okay, so meaning I need to get the closed loop transfer function. right? So this is the command. Closed loop transfer function is equal to feedback. Okay, feedback. System is our transfer function. So meaning here our system is G. Okay, and then the feedback is -1. Right? So this will be the closed loop transfer function, 5 over 0.5s minus 4. Okay, so you can check manually. It should be the same. Feedback, both, apa lagi? Okay, I think that's all. The thing, basically there are many, but there are many other functions that you can use. But I think these are all the function that is related to what you have learned so far, right? You have learned about time response. Okay, you want to see how the system responds when you apply the step input and impulse input. So you can type the command there, provided you know the transfer function of the system. Right, so you need to be able to define the transfer function of the system. Right, once you have the transfer function of the system, then you can do the all the analysis, whether the time response analysis, such as step input and also impulse input, and then you can do the stability analysis, which is root locus, and then frequency analysis, Nyquist and Bode plot. Right. I think I will stop here for the MATLAB. I'm going to continue with the Simulink, right? So other than a function in MATLAB, we can also use Simulink. Okay, Simulink is a graphical representation, okay, for a system. Okay, it's like you draw a block diagram on paper, but now we are drawing on a software there. Okay, so we can draw as if we draw in the paper, and then we can simulate the behavior of the system. Okay, all right, so in order to open the Simulink, all right, so you can click the Simulink here. There is on the top here. All right, there is a logo Simulink. At home tab, and make sure you click on at home tab. Okay, then there is a Simulink. Okay, you can click that one, or you can also type Simulink. Okay, if you type the Simulink, it should open the Simulink Simulink interface. Okay, so that is where we draw the block diagram, and then we simulate the behavior of any system. Right, step longer time. Right, so this is the Simulink environment, right? Right, so you can, this is new, where we're going to create a new, maybe a blank model. This is what we're going to do today. Okay, maybe you want to create a library. Okay, a library is a collection of many functions. As a standard function, there is already library, but if you know how to create a library, you can create your own library so that you can use in any other project that related to the library. Okay, or maybe you want to create a project. Project is a combination of many model. All right. And then there's also more folder to project to GitHub, project for SVN, code generation, and digital filter. Okay, this is the advanced one. Right, so as for the beginners, we're going to create the model from blank canvas. So let's click that. Okay, it should open a blank canvas. So that is where we're going to draw the block diagram. right? So this is the blank canvas. All right, so you can see here there is a file. Normally file you want to create a new model, new chart library, and etc. Okay, you can open, save, export, print, setting the preference, and exit. Okay. Right, in edit you can undo, redo, cut, copy, copy to clipboard. Okay, select all, look at table editor, and etc. All right, and then this is normally view. You want to set whether you want to see the toolbar or not. Okay, status bar or not. Okay, explorer bar. Okay, so it's depend on your preference. Normally all these toolbar is to allow you to easily access to the whatever function that you want. Okay, so here okay, on display, we display all the blocks, all the error and warning, signal import. You can edit the signal import. Okay, all right. There is the diagram. Okay, the diagram is actually the diagram that you have plot, so you can format it. Okay, you can change the font style, foreground, background, connector width, right? You can rotate, you can flip. Okay, you can arrange. Okay, you can rearrange your block. You can create mask. Okay, you can create a user mask, meaning your own mask, so that you represent your system. Okay, signal and scope, right? And this is where we simulate the your model. Okay, you can update your diagram. You can do the model configuration. You can select the mode. Okay, data display, and etc. Okay, basically we already take out the toolbox here, so we can just use the function that is showing on the toolbar here. All right. Sekejap. Okay. All right. So in order to start drawing a block diagram, okay, first you need to have the library. Okay, so there, okay, on the toolbar here, okay, there is a library browser. Okay, so you need to click this library browser. Okay, so it will open a library. So the library contain all the function, all the block diagram, all the block that is already developed as a Simulink block. Okay. So let's start with commonly used block here. So this is among the block. Pardon?
Doktor tengah share screen ke?
Tak share screen tu.
Tak nampak.
We can see what's on screen.
Okay, you nampak muka saya?
Yes.
Okay. Dari tadi ke?
Tak,
Baru je.
Baru je.
Okay. Okay. Okay, now you can see the Simulink canvas, right?
Yes.
Okay, all right. So in order to draw a Simulink diagram, right, we need to have the library. Mana saya punya library? Okay, right. So you need to have a library. So you can click the library browser here. Okay, can you see the on the toolbar there is library browser. I'm moving the cursor over it. Okay, so you need to click the library browser. Okay, so it will open all the library. Okay, so you can see here this is the library for Simulink, meaning this is the common block for Simulink. This is the earliest version, and then you can see there is also a Simulink for the communication toolbox. Okay, if you are working on the computer vision, okay, so there is a block for computer vision, right? There's also toolbox for the control toolbox. Okay, we are working on the state estimation, linear parameter, linear time varying system. Okay, deep learning. Okay, so Simscape. Okay, Simulink 3D animation, Simulink design optimization, Simulink extras. Okay, this is additional one. Okay, but for us, for the beginners, normally we just focus on the Simulink here. Okay, just close all that. Right. So normally we focus on the block under Simulink. Okay, so this is the under commonly used block. You can see all these block that is popular when you're developing a model. Okay, for example, summation point. Okay, so if you want to use that summation point, you just click the summation point and then drag to the canvas. Okay. Right. Let's say I also want to use gain. So I'm going to click the gain, right click, and then I'm going to drag that. Okay, drag and put that in on the canvas. Okay, so that's how we create a block diagram. Okay. Okay, so under continuous, okay, this is all the block diagram that represent for a continuous system. Okay, so we have integrator. Integrator is one. Integrator is 1 over D lah, 1 over D. S is the differentiator, S, but 1 over S is the integrator. And then we have PID controller. Okay, we already learned PID controller last week. We have transfer function. Okay, so you can use transfer function here in order to simulate the transfer function just now. Okay. All right. Then the popular one is sources here. Okay, sources is the input actually. All the block here is the input type block. Okay, whether your input is band limited white noise, clock, only a constant input, maybe it's coming from a file, okay, coming from a workspace in MATLAB, coming from the spreadsheet, okay, and of course the popular one is our here, step input, okay, RAM input, okay. There is no impulse input in here, but you can combine 2-step input to become one impulse input. Or you can also use signal builder, signal editor, or signal generator in order to generate your own signal. All right. So let's try use this one. Okay, in order to delete, you just choose the block that you want to delete and then push the delete button. All right, so let's try let's try to simulate the response that we simulate in MATLAB just now, right? So we apply a unit step input. Okay, that one we leave there. And then we apply unit step input into the transfer function, and then we're going to plot that. Okay. So in order to do that, we need to get the output, okay, which is from the sink here. Okay, so normally you can commonly use block continuous, sink and sources, and then there is also math operation. Okay. Right, but for now we're going to plot that, so I'm going to use scope. So I choose the scope, and then I'm going to drag it here. Right. So this is the right. So this is our system transfer function. We apply the unit step input, and then we want to see the behavior of the system. Right. So let's define our transfer function. Our transfer function just now is 5, right? And then this one here is 0.5, right? Okay, so we're going to apply and okay, right? So you need to set up the step input. Okay, step time is 1. This is meaning that the step will occur at 1 second. Okay, but ours is will occur at 0. Okay, so initial value is 0, meaning time 0, the U is also 0. And then the final output is 1. So this is unit step input. Okay, if your step input is 2, then put it 2. Right, so we're going to apply that. Okay, right. So we're going to simulate by clicking the green button here. Okay, you can see that there is run. Green button with triangle symbol there for run. Okay, and then we can change the time here. This is how long you want to simulate the behavior, whether you want to simulate for 10 seconds, 20 seconds, or 100 seconds. So it depends on your system. Okay, so I think for our system 10 seconds is enough actually. Right, so this is where we choose the simulator. Then normal is okay. Right. Okay, basically that's all the setting that we need to do. So, right, so just click the run button here. Okay, if you click the run button, okay, if you hear the sound that, meaning your simulation has done. Okay, so you can click the scope there. Okay, we open a monitor, right? Right, so basically this is the the same plot as the one that when we use MATLAB. Okay, it will settle at 1, right? And then it will settle at 5. Okay, 0. We apply unit step input. Gain is 5. Okay, so it settled at 5, and then the time constant is 0.5. Okay. If you want to check the data, okay, we can check the data. Okay, you can use Pickfinder. Okay, normally we just use the measurement data here. Slow. Let me slow. Okay, we're going to use the cursor measurement data. Okay, So we can move the cursor. Okay, so you move your cursor to the line here. Okay, so you can move the line so that you can see, you can read the data. Okay, so for example, you already know that the time constant is 0.5. So you can move the cursor by moving the line and then go to 0.5 to read what is the reading there. Okay, I'm going to move that up until you can read. You can also read from the value here, cursor measurement, while you dragging that. Okay, so it should be the time is 0.5. Okay, that is 0.48, 0. I think that is the closest one actually, because the data also has a snap point. Okay, I believe that is the closest one then. Okay, 495, 404, and 504. Okay. So you can choose 504. So the value is 3.143. Okay, 3.4143. Okay, so that is the value. I think if you multiply 63.2% multiply with 5, you should get around that value. Okay, so and then same this one. You can click the line, make sure the black cursor. Okay, you can see that this is white cursor, and then if you move the cursor on the line, okay, you can see the black cursor there. Okay, and then you can click and move the value there. Okay, so we can consider that one to be the settling time. The settling time, where the time it reached the final value. Okay. On the scope, you can also zoom in, zoom out, pan. Okay, so if you zoom in, so you can you can zoom by moving the cursor. Okay, you can also choose from here. Okay, this is pan. Okay, so you can move your plot. Okay, apa lagi? Important. You can also copy to clipboard. Okay, if you copy the clipboard, it will copy the diagram here, but the background will be black. Okay, so it is better for you to plot in the MATLAB. The plot is much better, and you also can edit there. Okay, instead of copying from the diagram here. All right, so in order to copy that, you can use, okay, we can send the data to the MATLAB. Okay, so use sim out to workspace. Okay, so let's give a variable name. Let's see, data 1. Okay, and then you can take the signal that you want to plot there, so which is the output here. Okay, so if we run it again, okay, if we run again and then we look at the MATLAB, so here we can see the output here, Simulink output. Okay, so we can plot the data. Right. So data 1 here. Okay, I think we need to set up one more thing for easier to plot. Okay, you can double click workspace here. Okay, you can click double workspace here to workspace. Right, it will come out the block parameter. So that is the variable name, right? And then here for the save format, okay, normally we choose structure with time for it is easier to plot. Okay. Okay, I have not run yet. Let's try on the previous data. Okay, okay, now it is time and data 1. Let's try to plot that. Plot boleh. Time, data. Time, comma, data 1. Time, data 1. Okay. Right, that's why I changed to structure with time. Okay, so let's run our model. So now if we run the model, so the data will be saved in terms of structure and time. All right, so let's open the MATLAB. All right, so the name is still the same, out. But now the data is in terms of structure and time. So we're just going to choose signal. It's separate time and structure, right? Let's choose the value here, right? So we're just going to plot the variable, and the variable name is given in here. Okay, out.data1.signals.values. Okay, so let's write that out, that .data1 dot signals dot values, right? Okay, let's run this. Okay, plot. What we're going to plot is the data. Okay, out.data1 signals.value. If you don't know the variable name, just look onto the name on here. Okay, this is the name of the variable. So we're going to plot that. Okay, so this is the response. Right. So if you plot in MATLAB, okay, kita tak change ke tadi? Static put 0 kan? Okay, so if you plot in MATLAB, it is easier for you to edit, okay, to edit the diagram. Okay, later I will show you how to edit the diagram. Right, let's continue on the Simulink here, right? Okay, now I'm going to do the close loop. So the closed loop, here we have a summation point. Okay, and then the summation point is a plus and minus. Okay, apply. Right, and then you can also add let's say we're going to add you can use you add controller, but let's consider that the Okay, let's change, let's use gain. Okay, for the P controller, let's choose gain. Okay, gain here. If you don't know where is the location, you can also type at the enter search here. Okay, for example, you want to find for gain. Okay, search for gain, and then it will search, and then it will come out all the gain that you can use. Right. Right. Okay, and then there is a feedback here. All right. So this is the closed loop system. Okay, the closed loop system without any controller, because we consider gain is 1, right? And then if we run this, okay, we run this, if we look on the scope, okay, let's we apply unit step input 1, the gain is 5, it should go to 5, but now the system only give you 0.833. Okay, the value is 0.833. Okay, so okay, this is the system, the open loop transfer function. Okay, the system where without any feedback, okay, the system will respond like that. It will be able to reach 5. Okay, however, the response may be slower. Okay, and then you add a feedback controller system. Okay, you add a feedback system there. Okay, now the system become feedback closed loop controller, closed loop system. All right, and then we run the simulation, right? And then we want to plot it on the signal. On the we want to compare. So in order to compare, if you want to plot any data onto the existing diagram, you can use a command hold on. Okay, so hold on, it will hold the figure. Okay, it will keep the signal that has been drawn, has been plotted, and then it will plot another one on top of that. Okay, so now let's plot the same data. Okay, but now the data is for the closed loop system, right? Right, so if we look, all right, so we can see, okay, this is the open loop system, right? Let's change, let's add a legend there. So the first one is open loop. Right, and the second one is the closed loop. Closed loop. Right, so we can see the difference in behavior for the open loop and closed loop. Okay, now let's change P equal to 2. P equal to 2. Apply. Okay, run. And then let's plot it again. Okay, since the hold on command is still on, right? So I'm just going to plot it again. Right. I just repeat the command. Right. So we have a third line here, the yellow one. Okay. So this is for P equal to 2. And then let's try with P equal to, I don't know, 9 last time. Okay, plot it again. Right, we have a purple one there. Purple one. So that is P equal to 9. Right, but still, okay, let's try one more because our desired value is 5. Let's try P equal to P equal to 100, you know. Okay, again, plot it again. You can just, if you want to get the command that you have already typed before, you can just use arrow key. There's an arrow key in your computer. So just use upper arrow key. Okay, so it will, if you keep clicking the upper arrow key, it will go through to all the command history that you already typed. Okay. Or you can also choose from the command history here. Okay, here on the command history. Okay, you can choose. So you can choose any command that you can use that you already typed before. Okay, this is the same one. So let's just evaluate that. Okay, so basically it will plot the data, but now the data is the for P equal to 100. Right, so you can see that it cannot, the system cannot improve the system to 5. Okay. Numerator 5. Okay. What else? Okay, let's use PID controller. Okay, so we're going to replace again here. Okay, let's choose PID controller. Okay, open the library browser. All right, library browser. So I want to use a PID controller. Okay, this one here. Right, so we're going to tune the PID controller. Right, so you can choose the controller from the PID. Right, so either to use PID, PI, PD, or just PI or I controller. Okay, P. All right, so let's choose PI. Okay, let's choose P equal to, I don't know, P equal to 100, and then the integral is 0.5. Okay, let's apply that. Then let's see the behavior. Alright. Let's plot it again. Okay, data 2. Okay, this is data 2. Kenapa dia tak begini? Ini dia tak masuk time ni. Mana? Final value 1. Let's check the closed loop transfer function. 1/s closed loop transfer function. Unstable. Okay. Off. Okay. Okay, it is unstable for the closed loop transformation. G is 5. -4, okay. Yeah, of course it will be unstable. Kenapa dia jadi -4? Okay, I think I know. Ini. Sepatutnya buang dari sini. Copy. Ctrl V. +1. Okay, different system is G. Alright, I think that this is correct one. Okay, step. Alright, so that is the response. Okay. Alright. Just now, when I show you the closed loop transfer function feedback system, right? The value here is not -1. It should be 1. Okay, because the feedback here is already represent negative. Okay, so you should use 1. Okay, closed loop transfer function feedback system 1. But if your feedback is positive, then only you put -1. Okay, so for a normal feedback, which is plus minus feedback, okay, so the constant here should be 1. Right, so that's why just now it said the system is unstable, okay, because it is plus. Okay, so the transfer function is this one here, 5/0.5 s minus 4. This will be provide unstable system. Okay. So the correct one is this one. Okay. Then we can see the response there. Okay, 0.5s, okay, plus minus, right, and then we already changed the P, PI, and etc. Right, and then let's say we want to use PID controller or PI controller, anything, right? Let's try this value. I don't know, I just put any value actually. Okay, let's say this is 1, this is 1. Okay, apply. Okay, and then we want to use auto tuning method. Okay, this is just a base macam kita anggarkan sahaja. Okay, starting point 101. Okay, and then we're going to tune using the automatic PID tuner. So here you can choose automatic tuning, select tuning method. We're going to use transfer function base. There are two type, transfer function base, which is for the time response, and there is also based on the frequency response base. Right, so let's just choose the PI transfer function, right, and then we're going to tune that. Apply. Right, let's tune. So it will open the PID tuner apps where it will tune the parameters. Right, so this is the okay, this is the response, right? This one, the dotted line is the when I apply 100, 1 and 1, okay, P is 100, I is 1 and D is 1. This is the response given by the system. Okay, block response meaning the one that we choose at first time. I set P equal to 100, I equal to 1 and D equal to 1. So this is the response, right? And then this is the response that has been tuned by the PID tuner, right? So right, of course you can change the type here. Okay, ini tak pernah di kemudian. Okay, if you want to change to PI controller or PID controller, you need to change at the PID parameter. Okay, you need to change at here. Okay, you need to change at here, right? If you want to use PI, PD or etc. Okay, once you choose that, the system will automatically tune based on the controller type that we have used, we have choose. Okay, all right, so here we can adjust. This is what we call as design requirement. Okay, so here the auto tune response here is based on the balanced response time. Okay, it is in the middle between slower and faster response, and then it is more toward robust response. Okay, as compared to aggressive response. Aggressive response meaning you can see many oscillation in there, but maybe the response time is faster. Okay, but this one is robust, meaning the system will not change very much to the input, but it's still able to reach at the final value. Okay, so if this the response here, the tune response here is not as what you want, you can change here. Okay, for example, you want a faster response time, right? So you can change, right? You can slide, okay, whether to choose slower or to choose faster. Okay, and then you can also change the transient behavior, whether you want to have a robust or you want to have aggressive. Okay, so that is the value that has been that is the response that has been auto-tuned by the system, right? So we can see the parameters, okay, by clicking at show parameters here. Okay, so the parameters, okay, you choose P equal to 3.3, I equal to 33, and D equal to minus 0. Something, right? And then this is the one that we choose. Okay, 100, 1, 1. Right. If you can compare the performance between the parameter that we choose as compared to the tune parameter, okay, we can see that the block response is better. Okay, it has a very fast response, right? And then there is no oscillation in that. Okay, but then it still depends on the system. Okay, whether your system require overshoot, and then you can see here this is the performance. Okay, in terms of rise time, rise time, okay, block is faster. Settling time, block is also faster. Overshoot 0%, this is 11%. Peak, okay, it does not reach peak 0.987. Then gain, this is in terms of frequency analysis, gain margin and phase margin. All right. And then this is the stability analysis. So the model is stable. Both provide this stable model. All right. However, normally it's quite difficult to get the value. This is, I think, a lucky guess there. All right. So we get this kind of response by putting the values. Okay. But somehow maybe our system cannot provide 100 here. So that will be the limitation. So so that's how we tune the parameters in order to get the response that we want, satisfying the design requirement and also satisfying the system itself in terms of hardware and software of the system. All right. Okay. Then you can also add a plot. Okay, you can use a frequency domain or time domain. Okay, so you can add a plot. Okay, let's say this is the plant response. Okay, this is the response of the system without any controller. Okay, 0, and then we go to 5, 5 unit step input, 5. But when we apply a closed loop, it will stable at 1 because the setting value is 5 at 1 multiplied by 5. Okay. Okay, then you can also add another plot. Open loop. Okay, that is the response for the open loop. Okay. Open loop without feedback for the system. Okay, this is for the tune 1. This is for the parameter that we choose. And then reference tracking is the error. Okay, reference tracking is the error. It is actually plotting this one here. Okay. That is the reference tracking. Okay, so this is the reference tracking for the P101 and 1 PID, right? So it is okay, it takes around 0.08 seconds to get the final value 2.32. Okay, other than that, you can also plot controller effort. Controller effort is this one here. Okay, let's if you want to compare one diagram into one plot, okay, you can double click the scope here. Bukan double click, right click. Okay, you can right click the scope here, and then you can choose signal and port, and then include another port number. So let's say I want to compare 2 signal together. Okay, so you can see there is another port here, right? So I'm going to compare the error with the control effort. Control effort is the output signal from our controller. Okay, if you run that, okay, you can see two line here. Okay, you can see 2 line, blue line and yellow line. Okay, you plot 2 graph onto 1 scope. All right. Okay, this is the control effort. Okay, control effort. And the last one is the ni tak ada lah ni, input disturbance rejection, output disturbance rejection. Okay, in term of frequency response, nak klik body plot ni tak boleh. Nak ikut ni. Macam. Okay, so basically this is how we use the auto tuning toolbox in order to tune the parameter. Okay, but you can use the value here, the tune value, as the reference. Okay, so that you can sometimes the response is not as what you want, so you can use as the reference and then tune a little bit on the parameters that you want, so that you provide provide better response. Okay. Okay, any questions so far? Okay, so far I've shown you how to use MATLAB command in order to do the time response, right? And then second one, we use Simulink. Okay, Simulink. You're going to draw a block diagram. Okay, and then you're going to do the time response analysis. And then if you add a controller, you can tune the controller using a try and error method or using auto tune toolbox. Okay, that's all based on the Simulink diagram here. Okay, any question? Because I'm going to give you a project based on the MATLAB. I'm going to give you a system, and you are going to do all this analysis. You need to draw a block diagram. You need to run the simulation. You need to plot. Okay, you need to do the analysis. You need to discuss the response, and then of course you're going to write a report on that. Basically, that is your assignment, your project. Okay. Any question? Anyone want to ask something? No one? Okay. Do you already download the MATLAB or not?
Yes, Doctor.
Yes. Lagi?
Yes, Doctor.
Taufik. Yes, shall we? Yes. All right. Okay. All right. All right. Yalah, dalam 30% ada kot dah download ni. Okay. So let's try to draw okay. All right. So this is a mass spring damper system. Mass spring damper system. Okay, mass spring damper system. You have a mass, you have a spring, you have a damper. I believe you already know the mass spring damper system, right? And this is the equation. Okay, basically this is MD square. If I'm going to rewrite that again, it's basically MD square X plus CDX plus KX equal to the equal to the input. Okay, so it is similar to you applying a small displacement to the spring or to the body. Okay, and then you release it, and then you want to see the response of the system. Okay, basically we already derived the transfer function. We already derived the time response. Okay, basically you should be you already know the response of the system. It is a second order system. All right. So now we're just going to use the Simulink in order to draw the block diagram of this system. All right. So okay, the reason why I rewrite the equation in terms of MA plus CV plus plus KX, okay, because this is the equation. Okay, the Simulink will be based on this equation. All right, so we're going to consider that the output is A. Okay, we're going to consider the output is A. A is MD, A is D square X. Okay, so A is equal to one over M multiply with FT minus CV minus KX. Right. So we're going to draw this block diagram based on this equation. Okay, the acceleration is equal to 1 over M multiplied with force minus CV minus KX. Okay, so we can see that there will be a summation point multiplying with 1 over M, and then we get A. Okay. Okay, right. Okay, so we're going to draw that. The equation is equal to gain, mana gain? Gain. This gain here is 1 over M. Okay. This is 1 over M. Okay. The output of this gain is acceleration. This is acceleration A. Right, and then the input to the acceleration is a summation point. Summation point tadi. Okay. Right, the summation point. Right, the summation point is the one of the input to the summation point is the input sources. Let's consider we use step input. Step input. Okay, step input. Right, and then the other one is CV. CV. Right, and then we need to add another one, so we can edit this one. So the sign is minus and minus. Okay. Let's adjust that. Say it is minus, plus minus, apply. Just want to change that. Mana. Yeah. Okay. Okay, that is step input, and this one here is KX. Right? All right. So that is the equation. However, we don't have X and CV, right? But we have acceleration. Okay, so in order to get velocity from the acceleration, we need to integrate. So we're going to use 1/s, the integrator. Okay, so the output of the integrator is the velocity. Okay, and then we have another integrator. Okay, and the output of the integrator here is the displacement. Okay, that is the thing that we want to display, the displacement. Here is the velocity. Right, this is velocity, this is displacement X. Right, so now we can complete that. Okay, so we have velocity multiplied with gain. Okay, that gain here, we're going to flip that. Flip the diagram, and then the value is C. Use capital C. Small C. Okay, and then this one here is okay. Okay, apply. Okay. Capital C. Apply. Okay. Right. So the reason why it is red here, because there is no variables in the system for K, M, and C. So later we're going to define that. All right. So for the displacement, we will connect to the, let's straight away connect to the workspace and also scope. Okay, let's use the same name just now, data one. So just copy that. And then change to the structure with time. Okay. So the step response is 0. Apply. Okay. All right. Okay, so this is how we draw a block diagram, right? So we have the acceleration. Okay, in order to get the velocity, we need to use integrator here. 1 over s, we get the velocity, and then we integrate the velocity, we get the displacement. Okay, it's quite different from the when we draw on the system on the paper, because we consider 1 over s is 1 over d square, d. Okay, d is s, 1 over d is 1 over s. Right, so we just kept that in this on paper. Okay, but on the Simulink we need to define that. So that term is 1 over s. Okay, so in order to simulate, we need to define the value of k, m, and c. Okay, so we're going to do that on the Simulink. Let's clear this. Okay, let's say m is 1 kilogram. K is equal to 1 and C is equal to 0.7. Okay, let's choose a value, right? So we can see that K is 1, M is 1 kilogram, and C is 0.5. Okay, then we can run the simulation. Okay. So this is the response, second order system. Okay, second order system. Right. Then you're going to do the same. Okay, you're going to do the same. You're going to plot. You're going to, if you're going to add a PID controller, then you're going to do, meaning the system here, we represent the system in terms of block diagram instead of represent that in terms of transfer function. Okay, you can also define this system as a transfer function. Okay, because here we have the equation here. It is 1 over m f minus cv minus this one will become s. This one will become, it's similar to like let's say it will become 1 over satu bagi adalah the combination tu, let's say it is 0.5 s square plus C bagi M berapa, you kira lah C bagi M, I just put numbers here plus let's say 5. Okay, so we get the transfer function basically. Okay, so you can use the transfer function block and define that. Okay, but if you already have this block diagram, okay, we can group this. Okay, I'm going to group this. Okay, this is the thing that I'm going to group. Okay, I choose it. I choose this system. Okay, and then put your cursor on any block, and then right click. Okay, right click, and then you can create subsystem from selection, or you can click Ctrl G. Okay, so if you click that, right, so this is my system. Okay, so this is the mass spring damper system. Right, so this is the spring damper system. If you want to see what is under this, you can double click, then it will show you the model. Okay, so this is the input port. Okay, where the input we connected to here, and then this is the output port. Okay, if you want to go back to the previous block diagram, you can choose this one, up to parent. Okay, we go back to here. Right. And then, of course, you can also edit that. Okay. Mosquito. Okay, you can change that. This is input, for example. Okay. Then you can also create a mask. Okay. Create a mask here. Okay, so you can draw anything on here. Okay, I mean you can draw. Let's say the system express mass spring damper, so you want to draw a mass and spring and damper on that. Okay, you can choose this. Okay, or you can also add an image. So you can choose any image. Okay. Okay, so I put schedule there, right? So we represent this as a mass spring damper system. All right. And then if you need to add a PID controller, so you will draw as PID controller. You need a summation point, you need a PID controller, and then you need feedback. Okay, so you will able to do similarly as before, as we what macam tadi lah, you draw a PID controller, then you tune the PID, auto tune the PID to see the response of the system, right? So basically, this is how we draw a dynamic system, right? Because you might not know about this 1/s here in order to get velocity and displacement. All right. Okay, I think I will going to stop here. If you don't have question, I'm going to prepare your project. Okay. And then you can expect all the thing that I've demo in here to be in your project. Okay, you should be able to draw a block diagram like this. Okay, you should be able to do the analysis in terms of time response analysis. Okay, because we already learned about time response analysis. Discuss the response and then plot the graph. Okay, maybe you need to compare the graph and etc. Okay. Last one, I think I haven't shown you how to edit. Okay, let's plot more. Okay. So this is the response. Okay, plot. Right, and you can edit, basically edit. Okay, let me see, because this is when you plot that, it's not based on time, it's based on the number of data. So basically you need to add time there. So let's see what is the signal for time. Data 1. This is time signal. Okay. So the command should be plot. Okay. For the x-axis, it is out data 1 data 1 dot time. Okay. Comma. Then this is the name for the y-axis variable. This is the name for x-axis variable. Okay, out dot data 1 dot time. Okay, that one. Okay, so if we plot that, okay, so now it is in terms of time. We simulate for 10 seconds, so it will simulate. It will show you in terms of time. Okay, so you can add the title. Okay, title. Okay, so the title is time response, for example. Okay, and then we can insert this is time in second, right? Insert Y label. This is displacement. Displacement X in 90 meter. Okay. You can also insert all this legend. Okay, legend. You can say this is for what? For system, meaning open loop system without controller. Okay. You can edit plot. Lambatlah respon dia. Dia tak keluar. Okay, you can change the color by selecting the line here and then right click. Okay, you can change the color. You can change the line style, whether you want to use dash. Okay, you can change the line width. Okay, you can change the marker type. Okay, let's say I want to use this one. Okay, you can change the you can add the grid. Okay, that one is on the canvas. Okay, you can copy, you can paste actually. Okay, and then marker size. Okay, maybe you want to have smaller marker size. Lambatnya nak keluar dia. I want to open this one. Lambat pula dia keluar. Inspector. Okay. Okay, so property inspector, basically you can do all that on the property inspector here. Data, legend, bukan yang ni lah, bukan property inspector. Okay, plot browser ke apa? Let's try figure palette here. Alright. Okay, so in figure palette, okay, if you need to add another plot, okay, you can arrange that either to put 4 plot in one diagram. Okay. Okay, you can change the arrangement there. Okay, basically you can copy and then you can paste here. Okay, you can add a 3D plot. Okay, you can add a text box. Okay, for example, you want to explain something. Pick one, for example. Okay, pick one. And then you want to add an arrow there. Pick one. Right? Okay, if you click on the scale, dia keluar ni dekat ujung sini. This one property inspector. Okay, you change the font. You can change the exist there. Sekarang dia punya ni macam advance sangat, so susah nak cari. Okay, alah, dia boleh tambah semua ni. Label. grid, ruler. This is all to edit all these things here on the graph. Okay. Okay, once you already done with all the editing, okay. Okay, you can copy. Go to edit and use copy figure. Okay, copy figure. And then you can go to Word and paste it. Aku tak ada pula Word ni. Okay, this is to help you in order to prepare your report. Okay, so we have this kind of diagram. Okay. Right, so that is the last thing that I want to show to you about plotting. Okay, you can edit your diagram so that your diagram is presentable. Okay, it is easier to edit in this MATLAB rather than to edit in Word actually, because in Word it will move when you edit it will move somewhere. If you want to combine it, you have to group it properly, right? So if your diagram is already edited in MATLAB, so you just copy and we paste in the Word there. Okay, I think that's all. That's all the thing that I want to cover. Okay, I've shown you how to use MATLAB to do the analysis. All right, I also show you how to use Simulink in order to draw any dynamic system, okay, or mathematical equation. And then we have seen the response, the scope, how to plot it in MATLAB, and then how to tune the PID PI controller. Okay, use PID auto tuner. All right, and then I'll show you how to edit your figure. Okay, I hope you can explore the plotting function there. Okay, so I think I will stop here. Assalamualaikum warahmatullahi taala wabarakatuh.